Our last conic section is titled Hyperbolas. In this lesson, we'll look at the key differences in the shape of a hyperbola versus circles and ellipses. A hyperbola is noted when there's a subtraction between the quadratic terms. Notice you can have x squared minus y squared or y squared minus x squared. Order matters. Make sure you recognize which variable goes first. The a squared term that's in the denominator is always first. So now we're not looking for the bigger denominator, we're looking for the first variable. Over on the right, we see the two different examples for shapes of hyperbolas. They'll be horizontal or vertical like ellipses, but notice they do not connect. They go in opposite directions. In our first example with the horizontal shaped hyperbola, notice x is first. So when x is first, the hyperbola will open up left and right. So you'll see that curve, it almost looks like a parabola or a quadratic function. It curves on the left-hand side and curves over here on that right-hand side. That's the shape of that hyperbola. Also, something to note in here, we've got those diagonal lines that are in red. Those are called asymptote lines. I know, what a weird word. An asymptote line is a line that a graph approaches but doesn't cross over. Please add that to your note packet. Again, when x squared is first, that's going to be horizontal. Over on the right, with y squared first, now our graph is vertical. And you'll see the curve opens up and down when y is first. Those diagonal asymptote lines are here as well. Now, like circles and ellipses, you can have a center at 0, 0 or a translated center, and that will affect the shape of your hyperbola. To sketch the graph of a hyperbola, we'll have to follow these key steps. The first thing you want to do is determine your center, and that's based on whether or not you have parentheses with your x and y squared terms. You'll want to determine your major axis, that will help you with direction, and your two major vertices. But we only have two vertices. We're not going to have four like we did with ellipses and circles. The b squared term underneath that second variable will help create a rectangle shape, which I know there wasn't a rectangle shape up above, but we're going to create a rectangle shape which helps us define the asymptotes or those border lines. All right, let's give this a try. Over on the right, graph each hyperbola, state the center and vertices, sketch in the asymptotes. If we look at our first example, x squared over 9 minus y squared over 16 equals 1. First, we know this is going to be a hyperbola because of the subtraction. That will be the indicator that it's automatically a hyperbola, not a circle or an ellipse. Because of that, the things we want to determine first are our center. And our center is going to be found with our x squared and y squared terms. Again, nothing's being added to them, so in this case, we'll start off with our center right at 0, 0. So that's pretty easy. Our second is to determine the major axis. Now remember, the major axis is always going to be the first variable, so it's not the bigger denominator anymore. Since x is first, the major axis is going to be the x-axis. And because the square root of 9 equals 3, we're going to count 3 to the right and 3 to the left, and that will be 3, 0, and negative 3, 0. Those are our major vertices. Let's go ahead and graph the center and the two major vertices. All right, so now for part 3, that kind of interesting part. For part 3, we're going to use our b squared to help create a rectangle shape. Well, b squared is 16. So if we take the square root of 16, that's going to equal 4. So from the center, and that's underneath the y value, I'm going to count up 4 and draw a little x. And I'm going to count down 4 and create another little X shape. Now, using the X's and my vertices, I'm going to create a rectangle that goes through all of those. So you can kind of see over on the left and over here on the right. So there's my rectangle. Now the asymptotes are actually going to go corner to corner on that rectangle. So the rectangle isn't the boundary, but the diagonals that we'll create are actually technically that boundary value. So from the center, I'm just going to count up with a diagonal and go all the way through to the top of my graph. And do the same thing in the other direction. And try your best to go right through those diagonals. I know it's a little bit off right there. Do the same thing in the other direction. These dashed lines are kind of the boundary for our hyperbola shape. That's literally how you create them. Mine's a little bit off, but there you go. That should be what we do to make that happen. I think this one over here is off. All right, anyway, we'll make this work. So that's all we have to do. I know, it seems kind of really strange. Remember, our vertices are on that left side and the right side on the x-axis. I'm just going to kind of make them bigger so that they're easier to determine. The hyperbola is going to connect through those vertices and go towards the asymptotes on each side. So it's kind of a nice smooth curve in that direction on the right. And then the same thing over here on that, whoops, let's try that again. On that left-hand side, we're going to just want to try to curve it right on through, connect that vertice, and then go in the opposite direction. And that's how you graph the shape of a hyperbola. Over on the right, we have y squared over 25 minus x squared over 10 equals 1. In this example, notice y squared is first. That means this is going to open up and down. It will be vertical. Our first thing to do is determine our center. And again, remember, x is supposed to go first in our center, but because it's 0, 0, we kind of get away with putting whatever number we want first, because they're both zeros. Our major axis is y, because y is first. So then to get our vertices, we go square root of 25, which is 5. If we go up 5, we'll be at 0, positive 5. Down 5 is 0, negative 5. Let's plot these 3 key points. And that's all really we need to plot for coordinates for our hyperbola. Now let's take a look at our asymptotes. We're going to create that rectangle again. Looking at the number that's underneath the second term, that's our b squared. It's 10. And if we take the square root of 10, that's not a perfect square. We'll have to approximate it at 3.2. That's the approximate square root of 10. What that means is we'll count, because it's underneath x, we'll count to the right and to the left. We'll go just slightly beyond 3 and draw a little x, slightly beyond 3 and draw a little x on the left. And now we'll create our rectangle. This will be a little bit trickier since we have to go just a little bit over 3 and down along that vertical to the bottom there, over on the right. And we're just going to do our best to sketch this in. It's kind of tricky with my pen here. All right, we'll draw that right down. If we're pretty close to 3, it is what it is. All right. Going from corner to corner, and we have to go through our center, will help us create our asymptotes, our border lines, and go all the way up to the top and all the way down to the bottom. Do that in the other direction, like so. And that's how we create our asymptotes. Now, there is also an algebraic method to do that, and you'll learn more about that in Honors Functions and Trig next year. This is just kind of the quick way to create those asymptotes. Remember, our major vertices are on the y-axis, and our hyperbola has to open up and down. The shape of this hyperbola isn't going to be quite as wide-looking as the one on the left. We're going to use our asymptotes as a guide, go through our major vertices, and then bounce in the opposite direction. And then we'll do the same thing, well, maybe, on the bottom. And notice it goes towards the edges. They don't curve back in. So make sure your graphs are curving towards those asymptote lines. So now to make things even more interesting, let's translate our center. The key thing to focus on here is identifying that very first step. Remember, your coordinate needs to be in XY form, so watch what variable goes first. And we get that right out of the gate in our first example for example 2. We have y plus 2 squared over 1 minus x plus 3 squared over 9 equals 1. So we know it's a hyperbola because of that subtraction in between the squared terms. Let's first determine our center. Now remember, our center has to be written x comma y. And in that format, notice it's x plus 3, so that would be minus 3. And it's y plus 2, that would be minus 2. There's where your center should be located. Our major axis is always what's written first, and that's the y-axis. So that means our vertices are going to go up and down the square root of 1, which is 1. Now what makes this unique is we have to move that from the new center. So we'll do negative 3, negative 2 plus 1, and negative 3, negative 2 minus 1. And that would give us negative 3, negative 1, whoops, and negative 3, negative 3. Let's plot those three coordinates. They're pretty close together, so make sure they're bold. Maybe use a different color just so that they're easy to see. All right, let's create step 3. Let's determine those asymptotes by creating that rectangle. Now remember, we always use that second number to create the rectangle. In this case, it's 9. So that'll be kind of nice. The square root of 9 is 3. And because it's underneath x, we'll go 3 to the right and create our x, and 3 to the left and create our x. Go ahead and draw a rectangle as best you can through those two x's and around the major vertices. So I created my rectangle and I drew in my asymptote lines all at once just because it was pretty particular getting through that rectangle. Hopefully your asymptotes look something like this when you draw them in. Now we'll create our hyperbolas. Remember, they should open up and down since y is first. And this will be a pretty wide-looking hyperbola since it's going to connect towards those asymptote borderlines. So swoop down, get to that vertex, that major vertice, and then make its way over to the right. And then do the same thing on the bottom, swoop up, connect to that vertice, and then, whoa, quickly trend away towards that borderline. So not quite as symmetrical looking just because the center had been translated. All right, everybody, I'd like you to try the next one. See if you can find the key features for this hyperbola. Complete steps 1, 2, and 3, and then press play and we'll graph it together. Let's see how you did. I found my center to be at positive 4, negative 2. And with my major axis, the x-axis, since it's written first, my vertices need to go to the right and to the left. The number underneath x squared was 9. The square root of 9 is 3. So I went 3 to the right, and that put me at 7, negative 2. 3 to the left put me at 1, negative 2. I plotted my center and those two major vertices. Then I looked at the number that was underneath y, and that was 16. The square root of 16 is 4. I counted up 4 and down 4 and drew my x. That helped create my rectangle. I connected the diagonals of my rectangle, and there becomes our asymptotes. Now the fun part. Let's sketch our hyperbola on the left side and right side of these borderlines. We want to swoop down on that left-hand side, connect into that vertice, and then back up in the opposite direction toward those asymptotes. And then the same thing on that right-hand side, kind of come down on that left, on that right, connect, and then loop over to the bottom. And there are our hyperbolas. All right, I think that's a good stopping point for now. We'll complete the rest of this video tomorrow.